This is Francis, Group J. I'll be presenting fraud detection in mobile money transaction, and I will be briefly explaining the dataset and the feature engineering phase of our project. We worked with a synthetic mobile money transaction dataset which contains over 197,000 records, including the transaction type, amount, and account balances before and after each transaction. During our exploratory data analysis, we discovered a major challenge. Only 8% of transactions were fraudulent. This class imbalance meant that a model predicting every transaction is as legitimate would still achieve over 91% accuracy, making accuracy alone a misleading metric. We also found that the original features had weak correlations with fraud, indicating that raw data alone would not be sufficient for effective detection. So to address this, we engineered a new feature such as balance change feature, transaction to balance ratio, and behavioral features like each account's average transaction amount. These features help capture unusual spending patterns and deviations from the normal user behavior. So by transforming the raw data into a more meaningful indicator, we provided our machine learning model with a stronger signal for detecting fraudulent transactions. So I'll be handing over to my next colleague who will explain how the imbalanced data set was handled.
Thank you, Francis. I'm Jonan, and I'll be taking us through how we processed our data and splitting and how we handled the class imbalance, as he has said. So how we handled our class imbalance, we introduced SMOT, and SMOT, how it did, uh, okay, like how it does it, it simply copies existing fraud examples. Instead, it looks at fraudulent transactions, and then it finds their neighbors in the feature space and then generates brand new samples which are similar fraud samples into along the line segments. So then from then it produces a realistic looking fraud example of a fraud pattern. So it produces realistic fraud example, and then sorry, how Smart does it, it produces a realistic fraud example of a data set on a training sample, and then it maps it to the nearest numbers, okay, the nearest data set. So to duplicate it to duplicate it, which reduces the risks of a model simply memorizing few fraud cases. So after applying SMOT, we did standardization using the standard scaler. So the standard scaler, why we did that, it was to make sure that uh, our mean uh, our mean becomes zero for all data samples, and then the standard deviation one. So then after doing that one, because it was critical for our neural network, because without it, features like transactions, which can go into hundreds of thousands of transactions, would dominate. So we had to go on to our next final thing, which was to choose between two feature selection processes. One, we chose sharp, and we used it to prune out features which neglected predictive contribution, and then we also used recursive feature elimination with cross validation to identify the optimum 14 features. Thank you. I will hand you over to our next presenter.
Thank you, Janan. I'm going to be, I'm Donata. I'm going to be taking you through the model development and optimization phase of our project. So we trained several machine learning models, including random forest and GX boost. So our baseline random forest achieved a fraud recall of 0.71, meaning it detected 71% of the fraudulent transactions. So while this is reasonable, it still allowed many fraud cases to go undetected. So GX Boost performed significantly better, achieving a fraud recall of 0.96. This improvement comes from how GX Boost works. So unlike random forest, which builds trees independently, GX Boost builds trees sequentially. So with each new tree learning from mistakes of the previous one. So this makes it especially effective at detecting difficult fraud cases. So to further improve performance, we used randomized custom CV to tune key parameters such as tree depth, the running rate, and the number of estimators. We then performed threshold optimization. So instead of using the default probability of zero point 0.5, we found that a threshold of 0.23 increased fraud recall to 0.97, which is 97%, while maintaining the same F1 score. So in practice, this means the model becomes more sensitive to potential fraud, which is desirable because the cost of missing a fraudulent transaction is often much higher than investigating a false alarm. So finally, five-fold cross-validation confirmed that the model was stable and reliable, achieving a mean F1 score of 0.9476 with very little variation across folds. Yeah. Let me give my next present.
Thank you very much, Donata. I'm Joel, and I'm going to continue from where she has stopped. We trained for models, random forest, XGBoost, soft voting, ensemble, and a multi-layer perceptron neural network. Yeah, so um, we based on the XGBoost baseline to develop the soft voting ensemble that combine the random forest and the tuned XGBoost. In soft voting, each model votes by probability rather than the hard class, and we average those probabilities. So we ended up finding that the precision was 0.46 and the recall was 0.78. Secondly, we developed the multi-layer perceptron neural network. Now this one, it had specifically two hidden layers with 64 and 32 neurons. Now to reduce or to avoid overfitting, we applied railroad activations and 20% dropout. So we came up with a 99.7%, that is the validation accuracy, while the training accuracy was 91.8%. So furthermore, when we wanted to find the contribution of each feature towards the final prediction, we applied the Shapley additive explanations, and we came to find out that type transfer alone accounts for approximately 95% of the XGBoost model predictive importance. Then the rest of the features contribute to the 5%. Thank you very much.
Then you're going to merge right now. You need to